Chapter 10 is also on chemical bonding. We're going to cover molecular shapes, VSEPR theory, and molecular orbital theory. So Lewis theory taught us about how atoms are connected together, why bonds form, that sort of thing, but it doesn't tell us much about the three-dimensional shape. And three-dimensional shape is essential to understanding biology along with chemistry. So, for example, here on this slide, I have all sorts of different sweeteners, which, if you look at them in 2 dimensions, look different from each other, but 3-dimensionally, they can all bind to the same sweetness receptors on our tongues, and it's that 3-dimensional molecular shape that gives it the part that tastes sweet rather than a single bond or something involved. So structure determines properties, as does 3-dimensional shape. So structure, so far we've talked about things like skeletal arrangement of the atoms, the kind of bonding, that ionic versus covalent determines the properties, but the shapes also determine the properties of a molecule. And so a robust bonding theory should allow you to predict the shapes of molecules along with those other things. So we're going to build on Lewis theory and explore VSEPR theory, valence shell electron pair repulsion theory. And what that says is that electron groups around the central atom will be most stable when they are as far apart as possible. And these resulting geometries will allow us to predict shapes and bond angles in the molecule. So rather than drawing things flat in 3 dimensions, we're going to work in, flat in 2 dimensions, we're going to work in 3 dimensions and think about shapes and bond angles between atoms. So here's a picture showing what that previous slide was saying. There's a central atom with these electron groups, and the electron groups spread out as much as they can in space to allow for the largest possible bond angles. Now, the Lewis structure that we can draw can tell us the number of valence electron pairs around the central atom. So when we're talking about electron groups, we are going to include a lone pair of electrons as one electron group, and another atom that the atom is bonded to is one electron group. So for instance, if we're looking at this nitrogen here, there's one lone pair and it's bound to 2 other atoms. So when we're working in 3 dimensions, we have to account for 3 things taking up space. A double bond versus a single bond does not matter when we are thinking about the things taking up space around an atom. It's just lone pairs and atoms. We don't worry about double versus single bonds versus triple. We have 5 basic geometries that we will talk through based on electron groups around a central atom. They are, so the 5 basic geometries, we can have 2, 3, 4, 5, or 6 things bound to a central atom. And each of these arrangements is we're going to have a word associated with it for the basic electron geometry. And it's important to note here that for molecules that exhibit resonance, it doesn't matter which form you use because the electron geometry is going to end up being the same. So first, our simplest one, when there are 2 electron groups, they're going to occupy positions on opposite sides. That's as far apart as they can get. This is a linear geometry because they're all in a line, and the bond angle is 180 degrees. So the two groups are as far apart as they can be, 180-degree bond angle. That's called a linear geometry. Our second option is 3 electron groups. If there are 3 electron groups, they're going to occupy positions in the shape of a triangle. That's called trigonal planar, and the bond angle is 120 degrees. So for here in our boron trifluoride, for our groups to be as far apart as they can, they have 120 degrees between them and they all fit in the same plane. It's called trigonal planar. For 4 groups, they're going to occupy the positions in the shape of a tetrahedron, which is what this shape here is. And our bond angle is 109.5 degrees. So 4 groups, tetrahedral geometry, 109.5 degrees. For 5 groups, they don't spread out exactly evenly. There are 2 positions. They can be the 2 positions. The first position is above and below the central atom. And then there are 3 positions surrounding the atom. Those are called axial positions. The top and bottom are axial. The other 3 are equatorial around the equator. Between the top and side and middle, this is 90 degrees, and then between 2 equatorial and the middle is 120 degrees. So there are 2 bond angles involved in the trigonal bipyramidal. And it's called trigonal bipyramidal because if you look at this shape down here, you can see 2 triangle pyramids stacked on top of each other. So trigonal bipyramidal. Then our last group is 6 groups around. That's called an octahedral geometry. And it makes an octahedron, which is a geometric figure that has 8 sides. All the positions are equivalent and all the bond angles are 90 degrees. So overall, we have the shape and the bond angle. So we go from linear is 180 degrees, trigonal planar is 120 degrees, tetrahedral, I should have another number of groups. So 2, 3, 4. Tetrahedral is 109.5 degrees. Then trigonal pyramidal is 120/90 for 5. And then octahedral, can't spell, is 90 degrees for 6 groups.